Слышно? Да. Вот.
Next speaker is Brav. It will be the unique token.
Если я говорю по-русски, мне кажется, будет сложнее вам, чем мне. Да, я пишу название. Let me write the title because I changed it a little. It's the same topic, but I changed the point of view to make it more in line with the rest of the conference. So the title is Shifted Symplectic Geometry. I'll explain what this is. And commuting Hamiltonians. And I'll start with something well known, which is Hitchen's Hamiltonian system to motivate everything. And when there are some new theorems, this will be joined with Nick Rosenblum. Okay, so I'm going to fix field of characteristic 0. This becomes important at some point. And to begin with, let's take a smooth curve, smooth projective curve. And I want to look at Higgs bundles on this curve. So I'm going to fix E, a rank R vector bundle. And a Higgs field on this, it becomes more complicated in higher dimensions. But on a curve, it's just a map from the tangent bundle, which in dimension 1 is the same as the anticanonical bundle, to endomorphisms of the bundle. That's all it is. It's just linear data. Call it phi. And in this case of a curve, because this is rank 1, this automatically gives, extends to a map from the symmetric algebra over the curve on the tangent bundle to the endomorphisms. So I can think of this as this pair E comma phi defines a module over the symmetric algebra. Hence a quasi-coherent sheaf on the total space of the cotangent bundle, which is the spectrum of this algebra. So I can think of a Higgs bundle either as some data purely on the curve, so a vector bundle together with this linear data phi, or as a special kind of sheaf on the total space of the cotangent bundle. And this will be important later, this point of view. And then I want to consider a modulized space of such data. So we're going to look at first the moduli space of rank R vector bundles on C. And given a point in there, I want to recall that the tangent space to this point, I want to remember the whole tangent complex. I also want to remember automorphisms, so and deformations. So I'm going to write this as R-HOM from E to E shifted by 1. So in degree 0 of this complex, you have X1 or H1 of endomorphisms, that's the deformations, and in degree -1 you have the tangent space to automorphisms. So that's the usual moduli space of vector bundles, and then we also have this moduli space of Higgs bundles. I'm going to call MH for Higgs. So this is the moduli of rank R Higgs bundles. So it's this kind of data, a rank R vector bundle and a Higgs field. And there's an obvious map from here to here, which just forgets phi and remembers the underlying bundle. And the fibers of this are just possible choices of phi, possible choices of Higgs bundle. So the fiber is Hom from T of C to endomorphisms of E. And I want to rewrite this a little bit using Serre duality. So I'm going to put the whole R Hom. So you would see the whole R Hom if you took some kind of derived fiber. So under Serre duality, I swap the two orders, and I introduce a twist by canonical bundle. So this is R Hom from endomorphisms of E to, well, now it's going to be T of C, tensor Kc shifted by 1. That's the usual thing for Serre duality and dual. These cancel out in rank 1. This is Kc minus. So this whole thing turns out to be R Hom from E to E dual shifted by -1. And that's nothing but the dual to this complex. So this is the fiber of the cotangent complex to the moduli space of bundles. And from this, so this is a heuristic argument, but from this what you can show is that this moduli space of Higgs bundles is the total space of the canonical bundle, of the cotangent bundle to the moduli space of vector bundles. So this is no longer true in higher dimensions, but it works just like this for a curve. Yeah, so I considered the moduli stack of bundles. The DG structure is not so very important in dimension 1, but it becomes more important later. So I mean, it's a smooth stack.
And then you don't care about stable.
No, I don't. You can put that in your imagination if you want, but it's not important for what I'm going to say. Okay, so we have this isomorphism, and in particular, that means that this moduli space of Higgs bundles has a symplectic structure, just the standard symplectic structure on a cotangent bundle. In fact, an exact symplectic structure. And so you can try to study the symplectic geometry of this moduli space. So this is symplectic. In particular, there's a Poisson bracket on functions. So I'll look at versus global functions. So this is Poisson. And there's a collection of natural functions on here. So we might like to construct some natural collection of functions and compute their Poisson brackets. So there's a map called the Hitch and Map. So these are constructed by Hitchin. And this is a fairly concrete thing. So it's a map from this Higgs moduli space to an affine space. The affine space, the underlying vector space, is just, it's a product of finite dimensional spaces. This will go from 0 to the rank. And it's sections of powers of the canonical bundle. And it sends a Higgs bundle to, so I can take powers of phi. So phi is a map like this. I can tensor it together a bunch of times. So I'll get a map from some power of the anticanonical to a tensor product of endomorphisms, and then I can compose all those endomorphisms to get another endomorphism. And that will give me a map from, and then once I do that, I can take a trace. So let me write it like this. This goes to a tuple, which is trace of composing this Higgs field a bunch of times. So that's the collection I get. The way I've written it, that will actually look like a map out of some powers of Kc minus into O, and you dualize to get a section of power of Kc. Is there something with which to wipe the board? What? Ah. Uh-huh. So that's a map. And in particular, I can take functions on the target, this affine space, and pull them back here and get a bunch of functions on the moduli space. This is an interesting map. It has some interesting geometry. So like a generic fiber is some abelian variety, which you can describe in terms of this data. And it will involve some cover of the curve and abelian varieties associated to that. But just for the functions, I could start out by looking at the linear functions and pulling them back. So the linear functions just live in the dual of this vector space. So and we can compute that by Serre duality. So this will be sum of H1. So this was P0 to R. This will also be P0 to R. But in Serre duality, there will be a shift. So this will be minus P, that's the dual. But then I have to twist by Kc, so there's a +1. Okay, so these linear functions by pullback map to the functions on the moduli space. And theorem of Hitchin. So let me call this map just star. The theorem is that the image of these linear functions commute. And in fact, they form a complete integrable system, so they Poisson commute. So this turns out to be a Lagrangian fibration. The fibers have half dimension. So in fact, this is a complete integrable system. And I want to rephrase this a little in a way that will generalize to higher dimensions. So I'll replace, well, there'll be two generalizations. I'll state it in a minute. But I'm going to rephrase this in a way that looks silly now, which will be important later. So a silly way to say this is that star is a Lie map. It's a map of Lie algebras where the source is abelian.
Excuse me,
yes.
Is the Hitch and Map surjective?
It is for this dimension, for a curve. In higher dimensions, there are various ways you can generalize this, and then it's interesting to determine the image. So there's a standard generalization of this to a higher dimensional variety, studied by Simpson and other people, which involves as a target symmetric differentials. And that one is not surjective. But I'm going to talk about a different generalization, which is probably also not surjective, but has an interesting symplectic geometry. Okay, so the aim is to generalize this in the following ways. So I want to allow my Higgs bundle to actually be a Higgs complex. Could be a finite length complex of vector bundles. And this generalization was also studied by Sasha Yefimov. So he calls it the non-commutative Hitchin system. To Higgs complexes and to C is going to be replaced by X. This is some smooth variety. Actually, I'll say projective, but for what I say today, that's probably not important. So maybe I won't say it. It's not important for what I want to say today. So X is a smooth variety of, say, dimension D greater than 1. So these are the generalizations I want to consider. And the first thing is the generalization of the moduli space.
So do you mean that you don't care that it's not compact?
I don't, for what I want to say today. For other things that one might want to say, it's important, but not today.
Meaning you will have some local construction.
Local on X?
Yeah.
Well, it will definitely be local on the cotangent bundle of X. Not on the cotangent bundle of, on the cotangent bundle of X. Okay. Okay, so first let me just say what the moduli space is. So remember, for a curve, to give the Higgs field, it was just a map from T of C to endomorphisms of the bundle. I could just put a complex here and take the endomorphism complex, that's fine. But in higher dimensions, I should require that if I take the second power, so this will be second tensor power followed by the composite. I should ask that to factor through Sim2. So this is a condition that this commute. Well, for a bundle, it's a condition. For a complex, it's some kind of homotopical structure. And so that will give E is a module over the symmetric algebra. So that doesn't come from free in higher dimensions. You have to give E this structure. So the moduli space, the Higgs moduli space here will be, this is the moduli of, if you like, so perfect, that's a finiteness condition on a complex, roughly means it looks like a finite length complex of vector bundles. So in this case, a smooth variety, it will be exactly that. So it's the moduli of perfect Higgs complexes. And you can rewrite that using this description as the moduli of compactly supported perfect complexes on the total space of the cotangent bundle. So that's the spectrum of the symmetric algebra of T. But concretely, it's just this kind of data. It's some kind of finitely complex of vector bundles on X together with an action of the symmetric algebra. So this is the moduli space, and this is not in general symplectic. There's again a map to the moduli space of compactly supported perfect complexes on X. That's one place maybe where I would like X to be proper, so that proper upstairs corresponds to proper downstairs. However, this is not the cotangent bundle to mx, the moduli of, okay, so for simplicity, let's just say proper. Moduli of perfect complexes. And so it's not symplectic in the obvious way. Nonetheless, it is symplectic in some generalized sense. So we're still going to have a game we can play with Serre duality. So the volume form on the cotangent bundle of X so let me call it just Y. So I can take the symplectic form, I can wedge it together the maximal number of times to get something on zero. I get a volume form. And that volume form gives me, in particular, an identification of, or a trivialization of the canonical bundle. And then I can use that in Serre duality for sheaves on the cotangent bundle. So then for E tilde compactly supported on Y, Serre duality takes the following form. Can people still see here, or should I go to the... Okay. So Serre duality will say the following. So I can look at X from this object to itself. I'll put in the shift by 1. That's what I need for the tangent space to this moduli space. And by Serre duality, which works because I have compact support, this will be x from E to itself, but now twisted by the canonical bundle shifted by the dimension of the total space, which is 2 times the dimension of the base, and then a dual. But this is trivialized by the volume form. So this is x from my complex to itself, dual, and shifted by, I forgot the 1, a shift by 1, right? Like that. Right, so if I get the signs right, this is 1 minus 2d. Okay?
One should become minus 1, right?
Minus 1. Yeah, thank you.
I may ask you about support of your coherent shifts on cotangent bundle.
Mm-hmm.
Are they mapped surjectively on the base?
I don't require this. It's not necessary.
Okay.
So in the classical case, that happens because I assume that on the base I get a vector bundle when I push it forward. But in general, I don't have to assume this. Okay. So what do I get from this? This identifies, so this was tangent. Yes. Okay, so this is, left-hand side is tangent to the tangent complex to the Higgs moduli space. This is the left-hand side of this sequence of isomorphisms. And the right-hand side, which use Serre duality and the volume form, this part right here is the cotangent complex, and then there's a shift by minus 2d. Mm-hmm. And I seem to have missed a 2 somewhere. Right. So let me fix this just a sec. So let me rub this out. Let me rub out the 1. So let me write this as, I'll fix this. So I have this. The left-hand side is actually t shifted by minus 1, because there's no shift by 1 here. Right. And this would be plus 1. Okay, so if I bring this 1 over, I get a 2. Okay, so sorry about the original sign mistake. Okay, so what you get out of this is a kind of meta theorem, or a theorem stated very vaguely that contains a lot of information. So this is the theory of shifted symplectic geometry due to Pantev, Toen, Vaquier, and Vitsotsi. So this grew out of mathematical physics and something that's called the AKSZ formalism, Alexandrov, Kontsevich, Schwarz, and Zaboronsky. So they were studying some kind of sigma models and trying to construct some kind of odd symplectic forms on these in supergeometry. So this is what the theory ends up looking like in algebraic geometry. So there, you should think of this as the analog of the symplectic form we had when X was a curve, but now there's a shift. I don't just identify tangent and cotangent, but up to a shift. So there is a theory of shifted symplectic geometry. So you can study all the usual things that you study in symplectic geometry. There are shifted Poisson brackets, there are shifted Lagrangians, there's a theory of deformation quantization. And in particular, they talked about this example. So MHX is shifted symplectic of degree two minus 2D. So the content of that is that a symplectic form is a lot more than just an identification of fibers of tangent and cotangent. It really has to be a closed differential form, and it takes some work to formulate what that means and to prove that point-wise, this point-wise data really comes from a closed differential form, a two-form of this shifted degree.
Do you mean that these higher pieces of the symplectic form come from third duality? Or?
They do, yes. But there's work to even formulate the problem, let alone to prove it. So you should just take this as heuristic evidence that you would like such a theory, and then you actually have to develop it. So what does it make sense? How do you make sense of closed two forms which have some cohomological degree attached to them? And how do you prove that you actually have one globally on the moduli space? So there's really some content here, but I hope this is enough motivation why there might be such a theory. And then the further theorems, I think will show that the theory really has some content. So we're going to be able to generalize this statement of Hitch. There's going to be some natural functions on the moduli space, and we'll be able to say something about their commutators. And we'll be able to do this at the chain level. Okay, so 20 minutes, 25 minutes? 15, okay. So it's a 50-minute talk? Okay. Okay, so how to get functions on this modulized space and their Poisson brackets. So here, associated to this symplectic form, there's a Poisson bracket on, it's a chain level bracket, so it's a differential graded Lie algebra. If I want it to be a differential graded Lie algebra, I have to put in a shift. So when I turn functions into vector fields using this symplectic form of some degree, there will be a shift between the degree of the function and the degree of the vector field. And where do I get a natural collection of functions? So let me give a baby case. I'm going to consider a simpler moduli space on which it's easier to describe how to construct functions. So I'm just going to take an associative algebra. And I'm going to look at a moduli space M of finite dimensional representations of this algebra. So the points over the ground field are just finite dimensional representations. And I'll define a map from the algebra to functions on this moduli space. And I'll do this by telling you for each element of the algebra what the value of this function is. So here, if I have a representation V, I need to tell you what the value of this function is. So an element R will go to trace of action of R. So for each representation, I can take my element R, I can act on this finite dimensional vector space, take the trace, that's the value of the function at that point. And because trace is cyclically invariant, this factors through R modulo commutators. Which I want to interpret as what's called cyclic homology of R. So in non-commutative geometry, cyclic homology is what is going to take the place of functions. Right. So the general context is the following. So you replace, we didn't have an associative algebra in this geometric setup. We had some category of sheaves on the cotangent bundle of X. And what was important about that category, a few things. One was that I had Hom complexes, so it's a differential graded category. And the other is that there was this volume form, which can be abstracted to a kind of volume form orientation on a differential graded category. This is what's called a Collabial structure. So given a differential graded category C with volume form or Collabial structure, actually, I'll get to that in a second. I don't need that yet. That's about the symplectic geometry. So given a differential graded category C, so for example, quasi-coherent sheaves on a cotangent bundle, this was our example, or representations of an associative algebra, there is a moduli space. I'll call it MC, which parametrizes compactly supported objects in C. So you can make sense of this in this generality. So for experts, these are the pseudo-perfect complexes. And there's a trace of action map. From the cyclic homology of this category to the complex of functions on this modulized space. So that in this case of an associative algebra, if I look at what just happens in degree 0, it's this. So there's a generalization of this to differential graded categories, and that works at the chain level. And now I want to introduce some symplectic structure on this moduli space. So now if C has a volume form or Collabial structure.
So you somehow drop the symplectic structure of the cotangent bundle.
I actually only care about the volume form on the cotangent model, but now I'm going to reintroduce it.
Oh.
So in this statement, this was very general. It worked for any associative algebra, any differential graded category. Here I'm going to reintroduce extra structure corresponding to the volume form on the cotangent model.
To the volume, but not symplectic.
Symplectic form's not important, actually, for this story. You should just think of this as some Collabial variety. It happens to come from a symplectic structure, but that doesn't play a role. Okay, so C, if C has a volume form or Collabial structure, for example, the usual volume form on the cotangent model of a variety, then let's say of dimension n. So then this moduli space always has one of these shifted symplectic structures. So this is the theorem with Toby-Diekerhoff. Then MC is shifted symplectic of degree 2 minus n. And so that actually takes some work, but it recovers this example in a different way.
What is n?
N is just the dimension of the volume form. So in this example, n equals 2d. So that's just about the existence of the symplectic structure. In terms of the functions that we construct in this way in computing their Poisson brackets, so in particular, the functions on this moduli space shifted form a differential graded Lie algebra. This is a differential graded Lie algebra. You could ask, what is it automorphisms of? So a Lie algebra ought to be a Lie algebra for a group. The group is kind of Hamiltonian automorphisms of this shifted symplectic structure. And how does this behave with respect to this trace of action map? This is the analog of this theorem of Hitch. So the second theorem, and this is with Nick Rosenblum, it's actually a few theorems, so I'll state it in parts. So the first part is that so the setting is the same. So C is a DG category with volume form of dimension n. Then first part is that, well, I know these shifted functions have a Poisson bracket, so I would like the corresponding shifted cyclic homology to also have a Lie bracket so that I can ask for this to be a Lie map. So the first part is that the shifted cyclic chains, this admits a structure of a differential graded Lie algebra, and differential graded Lie algebras can be described in terms of either automorphisms or deformations. In terms of deformations, this is controlling exact deformations of the category C with volume form. So if this were really just usual algebraic geometry, it would be like studying a variety with a volume form and considering deformations of the variety and of the volume form such that the de Rham cohomology class of the volume form doesn't change. Part B is that this trace of action map is a Lie map. So let me again, I already had a star, I'll call this double star. This is a Lie map. That's a lot of data because these are differential graded Lie algebras, and it's not easy to construct maps between differential graded Lie algebras, especially if you don't have explicit models. So this is just defined up to quasi-isomorphism. So that's something very general. It had nothing to do with a cotangent bundle. And this is very much not abelian. So we're not yet seeing some commuting Hamiltonians like we do in the original Hitchin system. So to see that, you can see something in this example here. So for C, quasi-coherent sheaves on the cotangent bundle of a smooth variety, there's a component of this Lie algebra which is abelian, and it has a geometric meaning. So for C, this, I can look at the Picard group of this cotangent bundle and add its Lie algebra. So as a complex, this is functions with a shift by 1. Okay. So the statement is that there's a natural map, modulo constants. There's a natural map of Lie algebras from this abelian Lie algebra to this Lie algebra of cyclic chains. And
do you see proper support of over X in your notation for C?
No. It has to do with the definition of the moduli space. The moduli space doesn't parameterize all objects of C, just those that have compact support. So the category has no support condition, but the moduli space does. Okay, so here I want to point out that this does two things. One, it's a chain level statement. These are differential graded Lie algebras. That's what makes it difficult. The second thing is this gives a different proof of Hitchin's theorem. It's a refinement because it's at the chain level. It's not just about H0, but also gives a different proof of that Hitchin's Hamiltonians commute. So in the original proof was gauge theoretic. So some infinite dimensional C infinity construction to compute the Poisson brackets. Here, we know that the Hamiltonians commute because we know that they come from the action of tensoring with line bundles on this space. So this is an abelian Lie algebra just because it comes from the Picard group, which is abelian. Okay, so I'll stop there.
Sorry, I didn't quite understand. What was this guy at the left-hand side?
So I could look at pick 0 of y. So this is some derived group scheme, derived group stack.
Pick our group, you mean?
Yeah, the Picard group, but considered, you know, with the proper deformation theory. And then I have its Lie algebra, which the underlying complex is just the shifted functions.
I see. And then when you compose this map with this map and the point B, this would be commutative, the image.
Yes, so that this will refine the composite of C and B will refine the usual Hitch and Hamiltonians in the special case that this is quasi-coherent sheaves on the cotangent model of a curve.
And how is it related to Sasha's approach?
So I think Sasha sees, you see something like cyclic homology, right? Maybe the interpretation of the particular component. Mm-hmm. 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 Mm-hmm.